Hi everyone, welcome back. This is Earth and Space Science 101 and I'm Stephanie Welch. We're going to continue talking about groundwater today. So this is the second to last lecture that's part of this unit. We're still on Unit 3, Earth's Water. And remember the last lecture we did, Lecture 17, was also on groundwater. So, okay, just a quick kind of recap of the way that I'm doing these couple of lectures here to start us off with. We're going to start with a general concept. Last time it was gaining and losing streams and how streams, surface water, are then tied into the groundwater system. Today we're going to do the same thing. We're going to start off with a general concept and then we're going to move into something specific that's going on in Louisiana. You just need to know sort of the generality of that specific thing that we go into, so don't try to, again, copy every word off of every slide. There'll be a couple of sum up slides when we finish that topic, that example of this general concept that we're going to do. Okay, so what we're going to start off with today is this general concept of springs. A spring is just a place where groundwater is going to flow out onto the Earth's surface. And it does so for a variety of reasons. It is mainly going to depend on the local geology, how deep the water table is, how much pressure the water table's under, and the rock type. So that's going to kind of be part of the local geology. So you get springs in all kinds of places, including Louisiana. So you have springs in Florida, you have springs in the Grand Canyon, you have springs around here, and they are all occurring for different reasons. So we can basically sum up these different reasons why springs exist into the following three categories, or the three types of springs that are going to form. One reason why springs are going to form is because of some very quick, abrupt change in elevation or rock type, or in some cases both. So basically, in layman's terms, that means that you're dealing with something like a cliff face or an abrupt sort of mountainside, maybe even something like a canyon or a road cut. So in all of these cases, you're going to have not only an abrupt change in elevation, this would allow for the water table to then just sort of exit out onto the surface, and you have water flowing off the side of this cliff or road cut or canyon. But you're also probably going to have a change in lithology or rock type as well. So take the Grand Canyon, for example. We know already that because we're dealing with northern Arizona, we're going to have a fairly deep water table, but that's from the perspective of being at the top of the Grand Canyon, at the very, not at the base of the canyon. So the water table in that area might be perched in places. The actual water table might be a little bit deeper, but you might have pockets of water existing maybe a few hundred feet below where the visitor center is in Grand Canyon. And so this water would then be able to just sort of exit right out onto the sides of the canyon and then flow down the walls of the canyon and empty into the Colorado River and become sort of a little mini tributary of the Colorado River. So it's the change in elevation that is allowing this to happen, in addition to the change in rock type, because that water is existing in some layer of rock or some strata that's going to be both porous and permeable. So maybe a sandstone layer would be where that perched water would be, and below it and above it you might have something like shale. So obviously that's not the reason why we have springs around here, so we have to kind of keep digging if we're going to look for the reason why we have springs in Louisiana. The second of the examples or sort of types of springs that might form would be when you have some sort of structural feature that's going to allow for springs to flow or for that water to move under pressure from the subsurface up to the surface of the Earth. So the structural feature is almost always going to be faults. And faults can act as natural conduits for the water to flow up to the surface, much like drilling a well under certain conditions allows for the water to flow up to the surface. An artesian well is the one that allows the water to flow without needing to be pumped. But faults can allow for this to happen without the intervention of actually drilling a well, but you only get water flowing up those faults when it's highly pressured in the subsurface. Maybe not currently, but in the past in South Louisiana, in places like Abita Springs and Denham Springs, Ocean Springs, Mississippi, Kentwood Springs, all of these places were named with the idea that there were springs there at the time when those towns were founded. And the reason why those springs exist is because of faults. So these faults in South Louisiana, they're allowing for that water to flow up to the surface. So in South Louisiana, our reason for having springs, at least in the past, under times when the groundwater was a little bit more highly pressured than it is today, it would definitely be under this second category of why springs form. The third one is pretty unique to places that have limestone in the subsurface, and this is definitely not the case in South Louisiana. We don't have any limestone around here. So places like western Kentucky, most of Florida, the Yucatan Peninsula, these are places where vast amounts of limestone exist in the subsurface. And limestone is this very interesting rock in that it can dissolve out with very slightly acidic water. So we're talking water that's definitely way less acidic than like a Coca-Cola. Water that only has a very, very slightly lower than neutral pH has this ability to dissolve out rock given enough time, given hundreds of thousands or millions of years. And so then these things called caves form. But when they're actively forming, they're below the water table. They're going to be submerged caves. So these same systems that allow for caves to form can sometimes connect up to the surface. And so springs in places like Florida are going to be really high magnitude springs. You're going to have a tremendous amount of water coming out of these places because you're not just dealing with a small fracture in the rock, you're dealing with a huge cave system essentially that's allowing for all that water to then flow up to the surface. So we're going to look at all of these different cases, cases 1, 2, and 3 in a little bit more detail. But we're going to focus primarily on first Louisiana groundwater and Louisiana springs and problems with groundwater quality in places like Baton Rouge. And then later on in the lecture, we're going to move to that sort of third case scenario where you have dissolved limestone and cave formation. So let's move to essentially sort of just case 2 for now, where you have structural features like faults that are allowing for the groundwater to flow. And we're going to look at, again, sort of the specific example of that, specifically what's going on in the Baton Rouge area. And really almost anywhere in Louisiana just north of New Orleans, the whole North Shore region, places like Hammond and Ponchatoula, and as far west as Baton Rouge, we're going to have these sorts of issues with groundwater coming up. So what we're going to talk about now is this feature in the Baton Rouge area and places east of there called the Baton Rouge Fault. And we're going to look at how that fault zone is going to sort of lead to this naming of all of these towns around here, all of this local geology, and we're going to see how the groundwater is going to be different in quality depending on where you are in proximity to the fault. So let's start off just kind of containing this idea just to Baton Rouge for now. And in this first picture, you can see that in the Baton Rouge area, we have this extensive fault structure. Now, there aren't a whole lot of surface expressions of the Baton Rouge Fault. This is mainly a subsurface feature, but you do have some places where you can see sort of the surface expression of the fault. And if you're from Baton Rouge, you might know the dog park that's in the Garden District, sort of north of the LSU campus. There's a big, big hill that I remember because I always remember going away from LSU and going uphill on my bicycle up this hill. And that hill is the expression, the surface expression of the Baton Rouge Fault. So the Baton Rouge Fault cuts east to west across Baton Rouge, basically sort of in the same vicinity as the I-10, I-12 corridor, so right along the interstates there. Now, north of Baton Rouge, of the Baton Rouge Fault, is where the city of Baton Rouge has drilled its municipal water supply. They drill into mainly something called the 1,500-foot aquifer. And north of the Baton Rouge Fault, you essentially have fresh water down to a really great depth, down a lot deeper than the 1,500-foot aquifer, down all the way to about 3,000 feet. And the municipal water supply of Baton Rouge is some of the best groundwaters and the best municipal water supply of any of the major cities in the United States. It's definitely far superior to New Orleans, which gets its drinking water from the Mississippi River. So you can even taste it just going to a restaurant in Baton Rouge versus New Orleans. You can definitely, at least I can kind of go in and know, yep, this is definitely Mississippi River water that I'm drinking here. So north of the Baton Rouge Fault, you have this deep, fresh water. But south of that fault, you only have a very thin layer of fresh water existing on top of salt water. And it's the fault itself that seems to act as this sort of semi-leaky barrier that's keeping all that salt water south of the fault and the fresh water north of the fault. Now, this has never really been a problem in the past because the salt water stays south of the fault, and north of the fault you continue to have fresh water very deep. But recently, it's become a little bit more of an issue with this fault acting as sort of a leaky barrier, allowing some of that salt water from south of the fault to flow through the fault and move to the northern part of the city and closer to the municipal water supply. So to understand this, we need to recap again the geologic history of South Louisiana and see why all the salt water exists, why all the faults exist, and then we're going to look at the sort of intersection of the two in the groundwater chemistry in Baton Rouge. So if you recall from previous lectures, like the lecture on oil and gas, a long, long time ago, we had a vast deposition of salt occur in the Gulf of Mexico basin. As North and South America disconnected and separated as part of the breakup of Pangaea, the Gulf of Mexico formed, but for a brief period of time, and brief in geologic terms is still like a few million years, but for some period of time, the Gulf of Mexico was a restricted basin. So all of the salt deposited on the floor of the Gulf of Mexico, as the seawater began to evaporate. Now, later on, as water that's a little bit more fresh, seawater from the rest of the world comes flooding in, some of that salt's going to dissolve away, but we still have over a kilometer-thick layer of salt at the floor of the Gulf of Mexico. It's called the Luan salt. So in the first of these pictures, you can see that imaged in red, the Luan salt. In the next few pictures, you can see how the deposition of sediment like sand and clay and mud is going to build all of these layers that we're going to stack up on top of that salt in the Gulf of Mexico. So successively, you start to fill in more and more of that basin and build out more and more of South Louisiana with all of these sands and gravels and clays, all of this siliciclastic sediment. And that's all imaged here in the stripe patterns, the polka dotted patterns, and so on. That's just basically all this sand, clay, mud. The important thing to remember is that, again, the salt is way less dense than the sand, the clay, the mud, the gravel. All of that sediment is a lot heavier. So then the salt wants to move up towards the surface, and you form these things called salt domes. Okay, so that's the part that is a little bit of a recap from previous lectures, like the oil and gas lecture. Now we have to add to it another sort of fundamental problem in South Louisiana, and that's this subsidence that occurs because of the packing of sediment along the coastline. This is a new thing that we're talking about now. So as the Mississippi River and other rivers in South Louisiana deposit sediment along the coastline, what happens is we pack the coastline so much that it becomes heavier so that it sinks down. And that process is called subsidence. So in order for this to occur, in order for the coastline to elongate and to allow for the sediment to be deposited on the coastline, a structural feature has to allow for that to happen. And the structural feature in this case is going to be these normal faults. Normal faults have the hanging wall moving down relative to the footwall. So as sediment loads on the coastline, these faults are going to allow for all of that sediment to sort of just slump down. So we don't get a tremendous number of like high magnitude earthquakes along these faults because these faults are through soft sediment. So you don't get the sort of high magnitude earthquakes that you'd expect in a place like South Louisiana. But what does happen is you get a little bit of coastal subsidence or sinking happening along these faults. So these faults are everywhere in South Louisiana. And to put it all together, I have an extremely busy graphic for you. So we'll take a second and unpack this. But what's essentially happening here is that all of these little squiggly lines across South Louisiana, the ones with these sort of little comb shapes on them, those are all representing faults. And the comb shapes are oriented towards the part of the fault where you have the sinking occurring, where the hanging wall is dropping down. So they're all oriented towards the Gulf of Mexico, and they're all east-west oriented because that's the orientation that you're essentially sort of building the coastline out towards. That's parallel to the coastline. So we have this tremendous number of faults, including the Baton Rouge Fault Zone, which, as you can see in this picture, extends from Baton Rouge itself all the way over, cutting sort of south of Ponchatoula and cutting right through Mandeville, right along the Lake Pontchartrain Basin. So that Baton Rouge Fault becomes important not just for Baton Rouge, but for all of us in the North Shore area above New Orleans. Also on this picture, in addition to all these faults, is the location of these salt domes. And like I've told you in the past, there are thousands of these salt domes, both offshore and onshore in Louisiana, and they're essentially the reason why we have an oil and gas industry here. The little red circles are illustrating in this picture where the salt domes are. So when you combine the two, you have the salt domes that are impacting our groundwater quality and the faults which are restricting where that salt water can then move to. So let's look at all of this along something called a cross-section again. So we're going to basically take sort of a slice out of the interior of the earth and look at what's going on with the groundwater chemistry along that slice. That slice is going to cut right through northern Mississippi, central Mississippi, through Baton Rouge, and all the way out to the coastline. But you could basically just take that line and pick it up and orient it anywhere north to south across South Louisiana. So you could move it over to where it cuts through Covington and Mandeville and New Orleans. You could have it cut through Hammond and Laplace and all the way out to the coastline, all the way out to Grand Isle. So you can really kind of pick it up and move it anywhere, and things would be basically the same. So as we look along that slice, this next graphic is showing you where the freshwater exists, and underneath that there's the assumption that you still have pore space, but all that pore space is going to be taken up by salt water. So saltwater and freshwater aren't going to divide quite as nice as easily as oil and water, but there's definitely going to be a difference in density. So while there's a zone of mixing between the two, you basically have areas of freshwater and areas of saltwater in the subsurface. And freshwater is always going to want to rise to the surface and be located closer to the surface, as we can see in this picture. So the recharge area for the Baton Rouge area, and really all across the sort of North Shore region, north of New Orleans and South Louisiana, the recharge for all of this is going to take place in central Mississippi in places like Jackson, Mississippi. So rainfall occurs there. You have the infiltration of that groundwater into the subsurface, and then it moves down dip, which means sort of along these layers of sediment, and then moves south, because all of this water is ultimately wanting to move out to the Gulf of Mexico. As it gets deeper and deeper and deeper, you get closer and closer to Baton Rouge. And then that water encounters the Baton Rouge Fault Zone. And what the Baton Rouge Fault does is actually forces all that fresh water to move up to the surface. So at this point, you have very highly pressurized deep groundwater water wanting to move up towards the surface. And the manifestation of that across South Louisiana is all of these towns with springs in the name, like Denham Springs and Abita Springs, Ocean Springs, Mississippi. All of these occur along or roughly along the Baton Rouge Fault Zone because that's what's forcing all that water to flow up to the surface. So south of that Baton Rouge Fault Zone, you don't have the freshwater very deep. You just have a little thin lens of freshwater existing on top of the saltwater. And it's not enough to supply most of the major cities of the far South Louisiana, like New Orleans, with usable drinking water. So therefore, you have to go with another source of drinking water. In the case of New Orleans, it's the Mississippi River. So, at least in the past, we know that you did actually have springs actively occurring, actively forming in South Louisiana, and you had all this fresh groundwater moving up towards the surface. And so in this picture, it's showing you, again, the southern limit of where the freshwater exists, the deep freshwater in excess of around 1,000 feet deep, and then where the saltwater is existing is anywhere below that. So it's not coincidental that below that extent of freshwater is where you have all of these salt domes. So the salt domes are a very likely and natural source of the salinity for all of this salt water that's existing below the Baton Rouge fault zone and other manifestations of that same sort of fault zone. So what we think is happening here is that in the Baton Rouge area, and this A to A prime cross-section is basically along the same line that that A to A prime cross-section was in previous slides, where you had the northern part, A, being around Jackson, Mississippi, and the southern part, A prime, being along the coastline itself, kind of right near maybe Grand Isle. So we know we have deep fresh water north of the fault, and then salt water existing south of the fault, and the specific salt domes that seem to be dissolving into the fresh water and causing all that salt water to exist there are the St. Gabriel and Darrow salt domes south of Baton Rouge. So we know that all that salt water is coming off of those salt domes, and then there's evidence that that salt water not only moves up, and it moves up because you have hot salt water coming off the top of these domes, so therefore it's less dense. It wants to rise up towards the surface, and then it wants to move north. So this is completely opposite of the direction that we typically think of groundwater moving, but groundwater at great depths do really interesting things because of essentially pressure. So the salt water is moving north. Meanwhile, the fresh water that's being recharged from the surface in places like Jackson, Mississippi, and moving down dip, it's then flowing out to the surface in places like Denham Springs and Abita Springs, at least in the past, at least in excess of 100 years ago. So conditions in the past were somewhat balanced because you had essentially the salt water moving north and moving up underneath the fresh water that was moving south, and then that fresh water exited out onto the surface and discharged out onto the surface naturally. So it's hydrologically balanced. It's a balanced system that's not going to allow any major changes to occur because the system is stable as it is. Now, we have to introduce the most recent part, or the recent complication, which is this issue of overpumping of the aquifer. Particularly in Baton Rouge, and due to the industries in Baton Rouge, like Dow Chemical, all of the other major industries that have popped up along the river itself that use the groundwater because it's a little bit cheaper for them to use groundwater than Mississippi River water for their industry. They have really complicated the process of overpumping in Baton Rouge, and that in combination with the municipal water supply has created an imbalance. So you add in the secondary complexity here of withdrawal by pumping, and then you have a problem because all of a sudden you aren't keeping this system in balance anymore. You're drawing out too much water. It takes the pressure off of the deep fresh water, so it doesn't flow up to the surface anymore and create springs like Denham Springs, which is why you don't actually see a spring in Denham Springs anymore, or Abita Springs. And it puts so much pressure on the deep groundwater that you're actually drawing salt water across the Baton Rouge Fault, which is why we see that salt water extending further and further and further north every year, getting closer and closer to the municipal water supply, which means you have to either move the municipal water supply to the Mississippi River or to another layer of the groundwater system where you're only going to continue to have the same problems. So I guess the sort of sum up with all of this is that while Baton Rouge doesn't have a problem with groundwater quantity, we are going to have a problem, and we already do have a problem, of groundwater quality because of overpumping of the aquifer. Taking the steps to legislate against having these industries pull water from the groundwater system and not the Mississippi River, to spend that little bit of extra money pulling that water from the Mississippi River instead of the groundwater system, would go a long way towards solving part of this problem. So, okay, I promised you a little bit of a sum up slide after, or a couple of sum up slides after all of that stuff about the Baton Rouge system. So, to kind of paint you that big picture, we're still just looking at a specific example of springs in South Louisiana. So, the cause of those springs, again, is faults in South Louisiana acting as a conduit for groundwater to flow up to the surface. Overpumping has stressed the aquifer and causing those springs not to form anymore. What is happening specifically in the Baton Rouge area is that overpumping has pulled salt water from across the Baton Rouge Fault into the northern area of Baton Rouge, getting closer and closer to that municipal water supply, potentially putting the municipal water supply in danger of salinization. Okay, so now that we've kind of summed up all of that, we're going to move on to a different topic that deals with springs, at least in part. So one thing that we haven't talked about so far with groundwater is the existence of caves, giant springs, these things called cenotes, which is basically Spanish for giant springs in the Yucatan area. We haven't really talked about all of these features that deal with the dissolution of limestone. And before we get into all of these features individually, let's kind of introduce sort of a blanket term for everything dealing with the dissolution of limestone. When we're dealing with caves, caverns, springs, sinkholes, all of these things are examples of something called karst topography. Karst is a Slovenian word, and Slovenia is basically sort of the capital of karst topography in the world, so they get to sort of invent the term for anything dealing with the dissolution of limestone. They have the largest cave systems in the world. And karst topography is basically going to be anything that deals with the dissolution of limestone. And really interesting things happen when you're talking about the groundwater system and when you get limestone involved. Because, of course, limestone doesn't act as something like sandstone or a conglomerate or even something like shale. All of those rocks, if they do contain groundwater, are going to have that water existing in the pore space between grains of sediment. In the case of limestone, it's mainly a crystalline rock, so there is no pore space to speak of, but if that rock is fractured, then that water can move through those fractures and actually dissolve out or widen those fractures over time. So you end up with either sort of places within that limestone that have 0% porosity or essentially sort of like 100% porosity. You end up with underground rivers, underground lakes, and once those areas dry out or the water table lowers, or the topography rises, then what happens as a result is that you have open passages underground, you have caves. And the vast majority of the time, 95% of the time, if you have a cave, it's a cave that is formed in limestone. Just to kind of cover all my bases here, there are some caves in the world that don't exist in limestone. You have caverns and salt deposits. The Bayou Corn area in South Louisiana is an example of a large cavity in a salt dome that actually collapsed the ground surface and led to a lot of destruction on the ground surface. You have things like essentially caves in places that are volcanically active, like in Hawaii, because you have these abandoned lava tubes. And you can even have something that's similar to caves existing in ice because of weird ways that the groundwater's flowing, or you can have caves existing in sort of a number of other environments, all dealing with sort of weird local geology. But for the vast majority of the time, if you're dealing with something like a cave or any kind of feature that looks like a cave, it's because you have limestone underground. Okay, so let's look at a map of the United States and see where these karst features are going to exist. Any of the karst features that deal with the dissolution of limestone on this map are going to be in green. So that includes almost the entire state of Florida. Florida is essentially one big carbonate platform that it only formed in the last 40 million years or so. You get places like some central and western Kentucky. Places like Mammoth Cave are going to be it's going to be a big karst feature. It's going to be a place where you have lots of limestone in the subsurface. Northern Arkansas, southern Missouri, places like in West Texas, and then in isolated places throughout the Appalachian Mountains and in the Rocky Mountains, all dealing with these folded layers of limestone that exist with other types of sedimentary rock. Now, you have other types of karst features that are mainly things like abandoned lava tubes and unconsolidated material where you have some karst-like features. Those are all pictured in red and yellow here. But as you can see, most karst features in the United States and worldwide are going to be dealing with the dissolution of limestone. So let's go ahead and define one individual karst feature that gets a lot of attention. That's going to be a cave or a cavern. For our purposes, we could basically use those terms interchangeably. A cave is basically going to be any passage underground that's big enough for a human to potentially be able to crawl through. And you'd be surprised at how small a feature you can actually crawl through. Even a full-size adult can actually get their body to move through underground. It gets a little scary, especially if you're claustrophobic. But this is essentially what a cave is. It's any passage that a person could climb through. Caverns typically are going to be a little bit larger, but for our purposes, we can use these interchangeably. If a cave is going to form, it's because at some point in the past, acidic groundwater has flowed through fractures in limestone, widening out those fractures over time, and then at some later point, either the water table dropped or the ground surface was elevated, let's say maybe because of mountain building or plate tectonics, something lifted up that all of those layers of rock to be above the water table. Because one of those two things happened, the water table is now lower than the dry cave, so you can actually walk through it or in some cases climb through it. A sinkhole is basically just some place where on the surface you have direct natural access to the cave. Most commercial caves, or even caves in things like national parks, are going to have some man-made entrances where you've drilled down, you've introduced some sort of place where you could build a stairway to get yourself into the cave system. But some of these entrances to caves are going to be natural features because essentially the surface, the top of the cave collapsed, allowing for the surface to move kind of directly into this sinkhole or this cave system. So that's essentially all a sinkhole is. That Bayou Corn thing that we were talking about earlier, this is sort of southwest of Baton Rouge. This is essentially a sinkhole that formed not within limestone, because we don't have any limestone in South Louisiana, but within salt. Because the Texas Brine Company was extracting the salt from this cavity, it introduced this place where the surface of that cavity was a little too weak and you had a collapse of the top, and you have all that destruction that went along with it. Most sinkholes, especially places where you have sinkhole provinces, where you have lots and lots of sinkholes, are going to be in places, obviously, where you have limestone. So there are plenty of sinkholes in Florida, in western Kentucky, some in West Texas. All of these places where you have limestone, inherently you're going to have places where those caves collapsed, creating these sinkholes. Now, something interesting happens with groundwater quality when you're dealing with these sinkholes. When you're dealing with groundwater that has to flow through something like sand and shale, those act as a natural filter for the water, so that when you're drilling a well underground, you're extracting that water, you can feel pretty good that that water is not going to be contaminated. Contamination happens a lot more rapidly in limestone areas because the water can flow directly into these sinkholes, and then that's then part of the groundwater system. So there's a time delay between the introduction of some contaminant into that sinkhole and then getting it into the groundwater system of maybe like a day before the entire aquifer is contaminated. This is especially a big problem when people use sinkholes as sort of natural landfills, and they start to throw old tires and things into these sinkholes, trying to sort of fill them up with garbage. That introduces all kinds of contaminants into the groundwater system. It can be a major problem. And so there are other types of features that we're not going to maybe define individually, but they're also very interesting as well. You have places where streams essentially just start running underground in places where you have a lot of limestone. This happens all the time in western Kentucky, and it's very weird to look at on a map. You have a river system that's flowing out onto the surface, and then it just goes to ground for a little while. And for several miles, this river might essentially just be flowing underground. And then it flows back up to the surface again. It moves as a spring up to the surface, and then you have a surface spring again. So streams tend to just disappear and reappear again. It's very weird. And then springs are going to be sort of a natural part of that, especially if you have maybe a larger river that's going to incise down and allow this access of this groundwater to flow directly into that stream. In the caves themselves, one of the reasons why people love to visit caves is for the cave formations. You get all of these really amazing, almost sort of flower-like formations. You get stalactites and stalagmites, and I won't make you remember the difference between the two, but stalactites come from the ceiling, stalagmites are from the floor of the cave. And you get all this amazing sort of flowstone, stuff that they call cave bacon, sometimes forming on the walls of the cave, and all of it happens essentially for the same reason. A dry cave passage is going to exist not in the saturated zone of the water system, of the groundwater system. It's going to exist in the unsaturated zone, or vadose zone, as you hear most often in cave geology. So in the vadose zone, above the water table, you still have plenty of water, but it's flowing downwards. It's flowing down to meet up with the water table and some of these deeper, sort of newly forming parts of the cave. So along the walls, you have all of this drip water flowing along the walls of the cave. It's dripping from the ceiling onto the floor. And what happens as a result is that mineral-laden water is flowing and dripping and precipitating out these mineral deposits. And those mineral deposits end up forming over really long periods of time all these fantastic cave formations. So in some cases, over maybe 1,000, 2,000 years of drip water in the cave, you might have a stalactite from the ceiling meet up with a stalagmite on the floor, all forming from this one single drip. And the precipitation of the minerals that are forming along this drip, they'll meet up in the middle and form something that looks sort of like a pillar or a tower in the middle of a cave system. So it's really fantastic to look at and to appreciate the amount of time that it takes for these features to form in a cave. So I used to actually work in a cave system. I worked in 2008 at Mammoth Cave National Park, and I got to experience some of the local geology in the cave system, and even some of the local biology in the cave system. Caves are home to some really, really fantastic species that exist only in caves and only in very specific caves, because as you move to a different cave system, you might have slightly different features on these organisms because of the geographic isolation. So the picture on the left here is of the Kentucky cavefish. He's really, really tiny. He looks bigger in this picture, but he's only maybe like 1.5 inches, 2 inches long. And he's completely sightless because you don't need eyes in a cave system. They exist on the tiny, tiny little bits of algae and other stuff that washes in with the water in the cave systems. So the other thing that gets really interesting to talk about in cave systems is when those caves are still submerged. Those are effectively sort of caves that are currently still forming. And you get high volumes of water coming out of those cave systems, outletting onto the surface, and then flowing into rivers. So particularly in Florida and in the Yucatan Peninsula, you have these giant springs, as you would call them in Florida, or cenotes, as you would call them in the Yucatan, that are all occurring because of all of this groundwater flowing out onto the surface. One thing to remember about them is that they're definitely very cold because all of this groundwater is coming from deep underground, but the water is perfectly crystal clear. And then all of that water then later flows out into rivers. Like in Florida, a major place where all of these springs are outletting to is in the Suwannee River in the Panhandle of Florida. So they're essentially sort of the newest part of this cave system that's forming, both because of a high water table and a low elevation of the ground surface. So the last thing I want to do with you guys today is take you on a little field trip to show you some of these giant springs and cenotes that I'm talking about. So I hope you enjoy this.